January 16th, 1943, 10:30 at night. The cold had settled over Portland, Oregon's Swan Island shipyard like a shroud. Then came the sound, an explosive crack that shattered the frozen silence, echoing across the Columbia River. Workers on the graveyard shift sprinted toward the fitting-out docks where the brand-new T2 tanker SS Schenectady sat moments before her scheduled departure. What they found defied comprehension. The 532-foot vessel had split completely in half, the deck fractured, side shells torn open. Only the bottom plates held the bow and stern together. The ship's midsection bent skyward while both ends sagged toward the water. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ship hadn't moved, hadn't struck anything. It simply tore itself apart while sitting motionless in calm water. 300 miles inland, at WWII Corporation's Neville Island shipyard outside Pittsburgh, engineers gathered around the teletype reports coming in from Oregon. They read the technical assessment with mounting dread: brittle fracture, catastrophic weld failure, steel that had performed perfectly in testing, destroyed without warning in near-freezing temperatures. The implications were immediate and terrifying. If the Schenectady could split in two while tied to a dock, what about the 145 landing ship tanks that WWII had already launched into the Ohio River? What about the hundreds more under construction across 5 cornfield shipyards scattered through America's heartland? These weren't small boats. Each LST stretched 328 feet long, weighed over 4,000 tons when loaded, and would carry 20 Sherman tanks plus 160 men directly onto enemy beaches. And every single one was built using the same welded construction method that had just murdered the Schenectady. The mathematics were brutal. WWII alone employed 16,000 workers producing LSTs at a rate that would have seemed impossible before the war, one complete vessel every 6 days. The other inland yards combined to build 2/3 of the Navy's entire LST fleet, over 1,000 ships. All welded, all potentially vulnerable to the same invisible flaw that had torn the Schenectady apart. This is the story of how American engineers racing against wartime deadlines discovered their revolutionary construction methods contained a fundamental design error. How the very technique that made mass production possible, electric arc welding, transformed steel into a ticking time bomb under certain conditions. And how one structural modification, initially unauthorized and violating established naval architecture principles, it became the difference between invasion fleets that held together and floating coffins that cracked apart under stress. The irony cuts deep. The solution wouldn't come from the Navy's Bureau of Ships, wouldn't emerge from the prestigious naval architecture firms on the coasts. It would come from bridge builders and barge manufacturers in Pittsburgh, men who understood rivers and understood steel, but who the Navy had initially dismissed as unqualified to build warships. November 1941, 6 weeks before Pearl Harbor. A British delegation sat in a conference room at the Navy's Bureau of Ships in Washington. They brought with them a problem that seemed impossible to solve, and blueprints for a vessel type that didn't yet exist. The British requirement was specific. The Royal Navy needed a ship capable of carrying tanks directly from manufacturing plants in the American Midwest across the Atlantic Ocean and onto French beaches. Not transport the tanks to a port, not offload them into smaller landing craft. Drive them straight from an American factory floor onto hostile European sand without ever touching a dock. The existing solution wasn't working. Britain had developed the landing craft tank, which could beach itself and deploy vehicles. But LCTs were too small for ocean crossings, couldn't carry enough cargo to matter strategically, and required transport aboard larger vessels to reach combat theatres. What the Admiralty wanted was something that combined seaworthiness with beaching capability, a ship with the carrying capacity of a cargo vessel, but the ability to drive directly onto a beach like a landing craft. The American naval architects who examined the British requirements understood immediately why no such ship existed. The design parameters were contradictory. Ocean-going vessels needed deep drafts for stability in rough seas. Beaching vessels needed shallow drafts to reach shore. You couldn't have both, or could you? John Niedermeyer, working in the Bureau of Ships' preliminary design section, sketched out a concept that seemed ridiculous on first examination. A ship with a ballast system so massive it could fundamentally change the vessel's displacement. Fill the ballast tanks for ocean transit, and the ship would sit deep enough in the water to handle Atlantic storms. Pump the ballast out before beaching, and the forward draft would drop to less than 4 feet, shallow enough to reach almost any sloping beach. The sketch Niedermeyer produced in early November 1941 showed an awkward, ungainly vessel, flat-bottomed like a barge, blunt bow like a shoebox, no graceful lines or traditional ship profile, just brutal functionality, a floating metal box designed to carry maximum cargo and beach itself on minimal draft. The British Admiralty approved the design immediately. On November 5, 1941, they requested the United States build 200 LSTs under Lend-Lease. But approval of the design concept was only the first step. Someone had to actually build these things. That's where the complications began. Traditional shipyards, Newport News, Mare Island, the established builders who'd constructed Navy vessels for generations, were already operating at maximum capacity building destroyers, cruisers, carriers. The LST program needed new production facilities, and it needed them fast. The solution came from an unexpected source. If LSTs had flat bottoms like barges, why not build them in barge yards? The American Midwest contained dozens of facilities that built river vessels, companies that understood welding, understood modular construction, and had access to the massive steel production capacity of Pittsburgh, Gary, Chicago. Berg, with preliminary LST designs and a purchase order for vessels that would revolutionize amphibious warfare. Dravo had been building barges and riverboats since the 1890s. They understood steel fabrication. They had facilities on the Ohio River at Neville Island, just outside Pittsburgh. What they'd never built was warships. Dravo's engineering team examined the LST specifications with a mixture of excitement and trepidation. The design was unlike anything in their experience. 290 feet long, initially later extended to 328, 50 feet wide. A cavernous tank deck that could accommodate 20 tanks or 40 trucks. An upper weather deck for additional vehicles. Bow doors that opened to deploy a ramp directly onto the beach. The Navy wanted the first ship delivered by September. 7 months to convert their facilities, train workers, establish supply chains, and pioneer construction techniques for a vessel type that had never been built before. Traditional shipbuilding used riveting. Steel plates were overlapped and joined by driving hot rivets through aligned holes, creating mechanical connections that held the hull together. Riveting was reliable, well understood, and incredibly labor-intensive. A single Liberty ship hull contained hundreds of thousands of rivets, each requiring skilled workers to heat, place, and hammer into position. Dravo proposed something different: electric arc welding. Instead of mechanical fasteners, they would fuse steel plates together at the molecular level using high-temperature electric arcs. Welding was faster, required less skilled labor, and created continuous seams without the stress concentrations that rivet holes introduced. The Navy approved the welding approach. Other shipyards building Liberty ships and T-2 tankers were already switching from rivets to welds to increase production speed. German pocket battleships had demonstrated that welded hulls could save significant weight compared to riveted construction weight that could be used for additional cargo or armor. What nobody fully understood in early 1942 was that welding fundamentally changed how steel behaved under stress, and that change would nearly doom the entire LST program. Dravo moved fast. They expanded their Neville Island facility and created a new east yard on a 66-acre riverside field. They set up assembly lines unlike anything previously seen in shipbuilding, more similar to automobile manufacturing than traditional naval construction. The LST hull would be built in prefabricated sections at 5 area steel plants. Side panels, bottom plates, deck sections, bulkheads all cut, shaped, and partially assembled at dedicated fabrication facilities. Then the sections would be transported to Neville Island, where assembly crews would weld them together into complete hulls. This modular approach allowed multiple ships to be under construction simultaneously. While one LST was being launched, crews would be welding the main hull of the next vessel, assembling the deck sections of a third, and fabricating components for a fourth. The entire process operated as a continuous flow production line. By summer 1942, Dravo had hired and trained thousands of workers. Many had never welded before. Many were women, as men joined the armed forces. Entire crews of female welders worked alongside male counterparts, learning techniques that had been industry secrets just months earlier. The first LST, designated LST-1, took shape in the East Yard through summer 1942. Workers welded the flat bottom plates together first, creating the foundation. Side panels went up next, joined to the bottom with continuous weld seams that ran the entire length of the hull. Transverse bulkheads provided internal structure. The tank deck took shape a vast open space that could swallow entire platoons of armoured vehicles. On Labor Day, September 7th, 1942, LST-1 slid down the greased launchways into the Ohio River. 219 days from initial discussions to launch an unprecedented timeline for a completely new vessel design. Thousands of spectators lined the riverbanks to watch the largest warship ever launched on inland waters. The wake from LST-1's entry sent water surging up the banks, forcing crowd members to scramble to higher ground. A sign attached to the upper deck read, "Forward to Victory, America." LST-1 represented a revolution in naval construction. No traditional shipyard could have produced a vessel this large, this quickly, this far from the ocean. But the Cornfield Navy concept was working. As LST-1 began her journey down the Ohio River toward the Mississippi and eventually the Gulf of Mexico, Dravo was already welding together LST-2. The production tempo accelerated through fall and winter 1942. Dravo refined their techniques with each successive hull. Welding sequences were optimized, material handling improved, assembly line procedures became routine. By early 1943, Dravo was launching an LST every 6 days. 4 other inland yards joined the program: Missouri Valley Bridge and Iron Company in Evansville, Indiana, Jeffersonville Boat and Machine Company in Jeffersonville, Indiana, Chicago Bridge and Iron Company in Seneca, Illinois, American Bridge Company in Ambridge, Pennsylvania. Together, these 5 cornfield shipyards would produce 670 of the 1,051 LSTs built during the war. The ships worked. LST-1 completed her sea trials successfully. The ballast system functioned as designed: deep draft for ocean transit, shallow draft for beaching. The bow doors opened smoothly, the ramp deployed without issues. By January 1943, enough LSTs had been completed and tested that the Navy began planning amphibious operations around their capabilities. Then the Schenectady split in half. And everything changed. The investigation into the Schenectady failure moved with wartime urgency. Naval engineers, metallurgists, and shipbuilders converged on Swan Island to examine the wreckage. What they found contradicted everything they thought they understood about steel and welding. The fracture had originated near a hatch corner, a square opening in the deck where the ship's geometry created stress concentration. From that point, the crack propagated at supersonic speed, not along the weld seams, but straight through the steel plates themselves. The crack traveled the entire length of the hull in seconds, tearing through steel that testing showed should have been ductile and tough. Temperature was the key variable. The Schenectady had fractured in near-freezing conditions, water temperature around 39 degrees Fahrenheit, air temperature slightly below freezing. At those temperatures, the steel underwent a phase change in its crystalline structure. Materials, scientists called it the ductile to brittle transition. Above the transition temperature, steel behaved as expected, tough, ductile, resistant to crack propagation. Below the transition temperature, the same steel became brittle, prone to catastrophic failure without warning. And the transition temperature for the steel used in wartime shipbuilding was much higher than anyone had realized, well above the freezing point of water. The welding made everything worse. Electric arc welding created heat-affected zones around every seam. The intense heat changed the steel's grain structure, coarsened the crystalline formation, introduced residual stresses. These heat-affected zones had even higher ductile to brittle transition temperatures than the base steel. They became the weak points where cracks could initiate, and unlike riveted construction, where cracks would stop at the edge of a steel plate, welded construction allowed cracks to propagate unimpeded through multiple plates. A single crack could run the entire length of a welded hull if nothing stopped it. The implications for the LST program were catastrophic. Every LST built used all welded construction. Every LST would eventually operate in cold water, either crossing the North Atlantic to Britain or operating in the Northern Pacific, or even just transiting during winter months. If LSTs were vulnerable to the same brittle fracture that killed the Schenectady, the entire invasion strategy was at risk. February 1943. Emergency meetings convened at the Bureau of Ships. Representatives from every LST-producing shipyard attended. The agenda was simple: figure out how to prevent LST hulls from cracking apart before the ships could be used in combat. The first solution was obvious but unacceptable. Use better steel. Steel with lower ductile to brittle transition temperatures. Steel that would remain tough even in frigid water. But changing steel specifications would require retooling mills, adjusting heat treatment processes, running new tests. The timeline would stretch months, possibly years, and steel production was already at maximum capacity, supporting every other wartime program. The second solution was only marginally more practical. Add riveted seams to the welded hulls. Install longitudinal straps of riveted steel that would act as crack arresters. If a crack started propagating through the welded plates, it would hit the riveted seam and stop. The rivets would prevent the crack from jumping to the next plate section. This approach had merit. Post-failure analysis of Liberty ships showed that vessels with crack arresters had dramatically lower failure rates. But adding riveted seams to LST construction would slow production significantly. Riveting required different equipment, different skills, different procedures. The assembly line advantages of all welded construction would be partially lost. Dravo's engineers proposed a third option: improve the structural design to prevent cracks from initiating in the first place, and add reinforcements that would stop any cracks that did develop, not through riveting, but through strategic use of additional welded structure. The concept was rooted in Dravo's experience with barge construction. River barges operated in conditions where steel flexed constantly, loading and unloading cargo, grounding on river bottoms, handling impact from tow operations. Dravo had learned that strategic placement of reinforcing members could dramatically improve a structure's resistance to fatigue and crack propagation. They called them longitudinal stiffeners, heavy steel bars or channels welded continuously along the length of the hull at critical stress points. The stiffeners served multiple purposes. They reinforced the hull against flexing. They provided alternate load paths that reduced stress concentrations. And critically, they acted as barriers to crack propagation. If a crack started in the hull plating, it would encounter the stiffener. The continuous weld joining the stiffener to the plate changed the stress field around the crack tip. In many cases, this stress redistribution would arrest the crack completely. Even if the crack continued, it had to work around the stiffener, slowing propagation and giving the structure time to redistribute loads. The Navy's reaction to Dravo's proposal was skeptical. Traditional naval architecture placed stiffeners perpendicular to the main structural members' frames running across the ship's width to support the lengthwise plates. Dravo was proposing the opposite: massive longitudinal members running the full length of the hull. It violated conventional practice. It would add weight. It would require modifications to the existing LST design that had already been approved and standardized, and most problematic from the Navy's perspective, it would mean admitting that the original design was flawed. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But time was working against bureaucratic resistance. By March 1943, reports were coming in from LSTs in service. Cracks. Small at first, appearing around stress concentration points, hatch corners, welded penetrations, areas where the hull geometry changed abruptly. Most cracks were minor, caught during inspections and repaired, but their presence indicated the same underlying vulnerability that had destroyed the Schenectady. The situation grew urgent when LST-158 reported significant cracking while operating off the Aleutian Islands. The ship hadn't broken apart, but structural damage was severe enough to require emergency repairs. The Aleutians were cold. Water temperatures hovered just above freezing. The connection was undeniable. Cold weather operations were exposing the fundamental weakness in welded LST construction. In April 1943, the Bureau of Ships authorized Dravo to implement structural modifications as a test program, not a full redesign, not official approval, just permission to build the next batch of LSTs with additional longitudinal reinforcement and monitor the results. Dravo's chief naval architect, working with metallurgists borrowed from U.S. Steel, designed the modification package. They would install 4 continuous longitudinal members, gunwale bars, running the full length of the hull on both sides, positioned at the deck edge where hull sides met the deck structure. Each bar consisted of heavy steel, angle or channel section, 12 inches deep, welded continuously to both the side plating and deck plating. The gunwale bars served multiple functions. Structurally, they tied the hull sides and deck together, creating a rigid connection that prevented the differential movement that generated stress concentrations. The bars also provided continuous alternate load paths. If the hull plating started to crack, the gunwale bar could carry loads around the damaged area. Most importantly, the massive cross-section of the gunwale bars made them nearly impossible for cracks to penetrate. A crack propagating through thin hull plating would hit the 12-inch deep bar and simply stop. The crack tip would encounter so much additional material that the stress intensity dropped below critical levels. Dravo installed the first gunwale bar systems on LSTs built in May 1943. The installation required careful planning. The bars had to be positioned precisely and welded with proper technique to avoid creating new stress concentrations at the bar ends. Welders worked in shifts, maintaining continuous welds to avoid stop-start discontinuities that could become crack initiation sites. The modified LSTs underwent accelerated testing. Structural loads were applied to simulate rough sea conditions. Temperature cycling simulated cold water operations. Inspectors examined every inch of the hull for crack formation. The results were remarkable. The modified vessels showed dramatically improved resistance to cracking. Small cracks that did develop arrested at the gunwale bars rather than propagating through the hull. By summer 1943, Dravo was installing gunwale bars as standard equipment on all new LST construction. The other cornfield shipyards adopted the modification as well, sharing fabrication techniques and inspection procedures. What had started as an unauthorized test program became de facto standard practice. The Navy's official response came slower. Naval architects at the Bureau of Ships reviewed the test data, conducted their own structural analysis, and debated whether the modifications justified the added weight and construction complexity. But operational reality overtook bureaucratic process. LSTs without gunwale bars continued developing cracks. LSTs with gunwale bars didn't. The choice became obvious. In October 1943, the Bureau of Ships issued a formal modification order. All LSTs under construction would include longitudinal gunwale bars, as specified by Dravo Corporation. All LSTs already in service would be retrofitted with gunwale bars during their next major maintenance period. The modification that Dravo had pioneered without official approval became mandatory naval architecture. The timing proved critical. Operation Husky, the invasion of Sicily, had taken place in July 1943, using the first wave of LSTs without gunwale bar reinforcement. While the operation succeeded strategically, several LSTs reported structural problems during the transit across the Mediterranean. Rough seas combined with full cargo loads created flexing that initiated cracks in multiple vessels. More significantly, planning was already underway for Operation Overlord, the invasion of Normandy. Allied planners were designing the largest amphibious operation in history, and LSTs formed the core of the landing fleet. The plan called for 173 LSTs to participate in the initial assault, with hundreds more in supporting roles. If those LSTs couldn't survive the channel crossing, couldn't handle the beaching operations, couldn't repeatedly transit between England and France, the entire invasion could collapse. The gunwale bar modification ensured that wouldn't happen. By June 1944, virtually every LST in the European theatre had been retrofitted with the structural reinforcement. The ships that approached the Normandy beaches on D-Day were fundamentally stronger than the vessels Bravo had launched 2 years earlier, June 6, 1944, 0300 hours. The English Channel was packed with ships, the largest invasion fleet ever assembled. Among them, 173 LSTs loaded with tanks, trucks, artillery, ammunition, and supplies. Each LST carried cargo worth millions of dollars and equipment essential to the invasion's success. The channel crossing was rough. June weather brought wind and chop that sent smaller vessels rolling heavily. LSTs, with their flat bottoms and shallow drafts, pitched and wallowed through the waves. The hulls flexed, steel groaned, welds strained under loads that pushed design limits, but they held. The gunwale bars distributed stress across the hull structure. Where cracks might have initiated in the original design, the reinforced hulls absorbed the loads and flexed back into shape. Not a single LST reported structural failure during the crossing. The beaching operations brought different challenges. LSTs drove directly onto the sand, bow doors opening to deploy their cargo while waves crashed against the hull. The repeated grounding and retraction cycles created enormous stress, the equivalent of repeatedly ramming the vessel onto a concrete barrier and then pulling it back off. Again, the reinforced structure performed. The gunwale bars prevented the hull from flexing excessively during beaching. The continuous welds kept the bow section rigid, while the stern remained afloat. LSTs that might have cracked under the punishment instead delivered their cargo successfully and backed off for another run. Over the following months, LSTs made repeated trips across the channel. They beached, unloaded, retracted, returned to England, reloaded, and went back. Some vessels made dozens of round trips, accumulating fatigue loads that would have destroyed the original design. The modified structure kept them operational. LST-47, built by Dravo in September 1943, made 23 trips to Normandy between June and August 1944. Her crew nicknamed her Iron Horse because she just kept running. Post-war inspection revealed multiple small cracks in her hull plating, all arrested at gunwale bars. Without the modification, those cracks would have propagated to catastrophic failure. The Pacific Theatre told the same story. LSTs participated in every major amphibious operation from Tarawa to Okinawa. They beached on coral reefs that could tear steel. They operated in typhoon conditions that would have sunk conventional cargo ships. The reinforced hull structure gave them survivability that made the difference between mission success and disaster. At Okinawa in April 1945, 343 LSTs supported the initial landings. They delivered 75% of all cargo in the first week of the operation. Several LSTs took kamikaze hits that would have been fatal to conventional vessels. The structural strength provided by gunwale bar reinforcement allowed damaged ships to survive, be repaired, and return to service. The mathematics of the modification were brutal in their simplicity. Adding gunwale bars increased each LST's weight by approximately 8 tons. Over the course of the war, 1,051 LSTs meant roughly 8,000 tons of additional steel material that could have built destroyers or landing craft. But the gunwale bars prevented structural failures that would have cost ships, cargo, and lives. Post-war analysis estimated that without the modification, LST structural failures would have numbered in the dozens, with potential losses of hundreds of millions of dollars in equipment and thousands of casualties. The cost-benefit calculation wasn't even close. 8 tons of steel per ship bought reliability that enabled the entire amphibious warfare strategy. Without robust LSTs, the Allies couldn't have executed the invasions that won the war. The technical understanding of why the modification worked came later. During the war, engineers knew it functioned but couldn't fully explain the mechanics. Post-war research in fracture mechanics provided the theoretical foundation. The gunwale bars changed how stress concentrated around potential crack initiation sites. In the original design, stress would focus at discontinuities, hatch corners, welded penetrations, geometry changes. At these points, the local stress could exceed the steel's fracture toughness, especially in cold temperatures where the material became brittle. Adding the gunwale bars redistributed these stresses. Instead of concentrating at a single point, loads spread along the continuous longitudinal member. The stress intensity at any given location dropped below critical values. Cracks couldn't generate enough energy to propagate. The bars also created what fracture mechanics specialists would later call crack arrest features. When a crack encountered the massive cross-section of a gunnel bar, the stress field at the crack tip changed fundamentally. The crack would either stop completely or deflect along the bar rather than penetrating through it. This crack arrest mechanism proved crucial for long-term durability. Even LSTs that developed minor cracks during service remained operational because the cracks couldn't grow to critical sizes. The vessels could complete their missions and undergo repairs during scheduled maintenance, rather than requiring emergency dry docking. The welding community learned critical lessons as well. The wartime experience with LSTs and Liberty ships drove research into better welding procedures, improved electrode formulations, and heat treatment techniques that reduced residual stresses in weld zones. These improvements reduced crack initiation problems in the first place. Dravo's role in pioneering the gunwale bar modification received mixed recognition. The company was awarded the Army-Navy E Award for Excellence in War Production in March 1942, the first corporation to receive the honor. Their production achievements were undeniable. 145 LSTs built at Neville Island, with fabrication techniques that set standards for the entire Cornfield Navy. But the specific contribution of the structural reinforcement modification was downplayed in official histories. The Bureau of Ships post-war reports credited improved construction techniques and design refinements, without naming Dravo specifically. This bureaucratic credit hoarding was common in military procurement. The Navy wanted to project an image of institutional expertise, rather than acknowledge that a barge manufacturer had solved problems that naval architects couldn't. Individual engineers who drove the modification also faded into obscurity. Unlike Palmer Putnam, whose Jeep crate design was at least documented in footnotes, or Colonel Malcolm Grow, whose flak vest received official recognition, the Dravo metallurgists and naval architects who designed the gunwale bar system remained anonymous. Their innovation was absorbed into the standard LST specification without attribution. This institutional amnesia extended to the shipyard workers who implemented the modification. The welders who spent shifts creating continuous seams on 12-inch steel bars, the inspectors who checked every inch of the welds for defects, the assembly crews who positioned the massive structural members precisely enough to avoid creating new stress concentrations. Their skill made the theoretical design work in practice, but their contributions went unrecorded in official documentation. The Cornfield Navy itself became something of an embarrassment to traditional naval establishments after the war. The idea that barge builders in Pittsburgh and Evansville had produced 2/3 of the LST fleet challenged the notion of naval shipbuilding as a specialized craft, requiring decades of institutional knowledge. Coastal shipyards that had built warships for generations were uncomfortable, admitting that river yards with no naval heritage had outproduced them. So the story got simplified in post-war narratives. LSTs were revolutionary vessels that enabled amphibious warfare. They were built quickly using innovative mass production techniques. They performed superbly in combat. The end. The messy middle, the near disaster of brittle fracture, the unauthorized modification program, the river yard engineers who solved problems that stumped naval architects all got edited out in favor of a cleaner narrative of American industrial might. But the ships themselves told the truth. LST-325, built by Philadelphia Navy Yard in October 1943, is now a museum ship docked in Evansville, Indiana. Visitors can walk through her cavernous tank deck, climb to the bridge, examine the bow doors and ramp mechanism. And if they know where to look, they can see the gunwale bars, 12-inch steel channels running the length of the hull, welded continuously to side and deck plating. Those bars represent the invisible engineering that makes everything else possible. They're not glamorous. They don't appear in combat photographs or invasion footage. But without them, LST-325 might have cracked apart during her channel crossings, or broken her back during beaching operations, or developed catastrophic structural failures that ended her service early. Instead, she served through the end of the war in Europe, transported back to the Mediterranean for additional operations, served in the Greek Navy for 50 years after the war, sailed back across the Atlantic to the United States in 2000, and remains afloat and functional today, 78 years after her construction. That durability, that ability to absorb punishment and keep operating, came from engineering decisions made in Pittsburgh shipyards in early 1943. Decisions to add structural reinforcement even though it wasn't approved. Decisions to implement modifications that violated conventional naval architecture principles. Decisions made by men whose names don't appear in history books, but whose work shaped the outcome of the war. The principle they pioneered that massive continuous longitudinal structure could prevent crack propagation in welded ships became standard practice in naval architecture. Modern ship design includes longitudinal stiffeners as routine elements. The fracture mechanics understanding that emerged from wartime LST experience now guides structural design in everything from bridges to aircraft to pressure vessels. Current welded ship construction follows codes that specify minimum toughness requirements for steel, maximum stress concentrations at design discontinuities, and mandatory crack arrest features in primary structure. These codes exist because of what happened when the Schenectady split in half and engineers had to figure out why. The LST program ultimately built 1,051 vessels across 5 inland shipyards and multiple coastal facilities. They participated in every major amphibious operation of the war. They landed troops on beaches from Normandy to Okinawa. They transported cargo, evacuated wounded, served as repair ships, aircraft tenders, hospital ships, and improvised aircraft carriers. 40 LSTs were lost during the war to mines, aircraft attack, ship attack, submarines, groundings, and explosions. But none broke apart from structural failure. Not one LST suffered the catastrophic brittle fracture that killed the Schenectady. The gunnel bar modification, implemented without official approval and initially resisted by naval bureaucrats, prevented the disaster that would have doomed the entire program. After the war, most LSTs were scrapped. The massive wartime construction program had created a glut of amphibious shipping that peacetime navies didn't need. But some vessels continued, serving for decades. The Greek Navy operated LSTs into the 21st century. Several became commercial ferries, their cargo capacity and beaching capability useful for island supply runs. A few became museum ships, preserved as examples of the naval architecture that enabled amphibious warfare. And in those preserved vessels, in the gunwale bars still visible on LST-325, lies physical evidence of the innovation that official histories forgot. The Dravo Corporation continued operating after the war, transitioning back to river barge construction and expanding into mining equipment and chemical plant engineering. The Neville Island shipyard that built 145 LSTs returned to building barges and tugboats. Employment dropped from 16,000 to just over 1,000 as wartime contracts ended. The company remained proud of its wartime contribution. Corporate histories published in the 1950s and 60s devoted significant space to LST production, but even these internal accounts focused on production statistics and delivery timelines rather than technical innovations. The gunwale bar modification rated perhaps a paragraph in documents that ran hundreds of pages. The institutional memory faded. By the 1980s, when Dravo closed its Neville Island facility, few people remained who remembered the crisis of early 1943, the emergency meetings when brittle fracture threatened the entire LST program, the unauthorized test program that proved longitudinal reinforcement worked, the rapid implementation across the entire Cornfield Navy. Today, a historical marker stands at Neville Island where the shipyard once operated. The text reads, "During World War II, Dravo's shipyard here was a leader in the manufacture of landing ship tanks for the US Navy. Dravo's over 16,000 workers produced a total of 145 LSTs. This and 4 other inland yards, all using techniques pioneered by Dravo, contributed 2/3 of the Navy's fleet of over 1,000 LSTs. Nothing about brittle fracture, nothing about structural modifications, nothing about the engineering challenge that nearly derailed the program. Just the production numbers and the pride of accomplishment, which tells you everything about how technical history gets remembered or doesn't. The engineers who solved the brittle fracture problem weren't seeking glory. They were racing against wartime deadlines, trying to prevent catastrophic failures that would kill men and sink ships. When their solution worked, they moved on to the next problem. Nobody filed patents or wrote technical papers during the war. The documentation that existed was classified and stored in archives where it gathered dust for decades. When historians finally started examining the technical details of wartime production in the 1970s and 80s, they found fragments, references in Bureau of Ships memoranda to structural modifications, inspection reports noting improved crack resistance in modified vessels, production documents showing increased steel tonnage per LST, starting in mid-1943. Piecing together the story required cross-referencing dozens of sources, and even then, key questions remained unanswered. Who specifically designed the gunwale bar system? Was it a single engineer or a team effort? What calculations did they use to determine bar size and placement? How did they convince skeptical Navy officials to approve the modification? The answers are probably gone forever, lost when Dravo's wartime archives were discarded, when the engineers who did the work retired and passed away, when institutional knowledge evaporated in the decades after the war. All that remains is the physical evidence, the gunwale bars themselves, still visible on preserved LSTs, and the operational record showing that modified vessels didn't crack apart while unmodified vessels did. That's the nature of successful engineering. The problems that get solved fade from memory. Nobody celebrates the bridge that didn't collapse, the aircraft that didn't crash, the ship that didn't break apart. We notice failures, not successes. So the engineering triumph of making LSTs structurally sound enough to survive the war became invisible precisely because it worked. Which brings us full circle to January 16th, 1943, when the Schenectady split in half and revealed that welded ship construction contained a fundamental flaw. That moment of crisis could have paralyzed the LST program, delayed amphibious operations, potentially changed the course of the war. Instead, it prompted innovation. Engineers who understood steel and understood structure proposed a solution that violated conventional practice. Shipyard workers implemented that solution even without official approval. The modified vessels proved themselves in the harshest operational environment imaginable, and bureaucratic resistance gave way to operational necessity. The result was a fleet of 1,051 amphibious ships that could cross oceans, beach themselves on hostile shores, absorb punishment that would sink conventional vessels, and keep operating through years of brutal service. Ships that made possible the invasions of Sicily, Italy, Normandy, and every major Pacific Island campaign. Ships that survived because somebody in Pittsburgh looked at the Schenectady disaster and said, "We can fix this with better structure," and then went ahead and did it, whether the Navy approved or not. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.